Given the velocity field for a 2D steady incompressible flow, the velocity is given as 3xy squared minus x cubed I plus 3x squared y minus y cubed j. Is the conservation of mass satisfied? Or alternative way of asking this question is this physically possible flow? Okay. If so basically if the conservation of mass is satisfied, what is the volumetric flow rate? And the Q is the symbol that we use between two streamlines that pass through 0, 0 and 1, 3. And the third component asks you find the velocity potential. Okay. In these type of questions, the first thing that I want to find is what is my U? Okay, U will be the one that has Ui plus Vj, right? So we want to first find that out. Okay, so velocity is equal to Ui plus Vj plus Wk. So from here I get myself my U is equal to 3xy squared minus x cubed, right? My V is 3x squared y minus y cubed, and from the question statement I got myself W is equal to 0. The first part of the question analyzes whether the conservation of mass is satisfied or not. For the question itself tells me that this is a 2D steady and incompressible flow, so my conservation of mass equation will be simplified to del U del x plus del V del y plus del V W del z. Is it really equal to 0? That's what we are assessing. Okay, so what I'm going to do is I'm going to go ahead and insert U to here, V to here, and W to here as well. Okay, let's just do it. Del x of 3xy squared minus x cubed plus del y of 3x squared y minus y cubed plus del z of 0. Is it really equal to 0? Okay, the last term drops out, right? So let's look at the first term. I'm gonna get 3y squared minus 3x squared, right? That's the first term, plus the second term, which I will get 3x squared minus 3y squared. Is it really equal to 0? So let's take a look. You can see that these 3x squares cancel each other because one has a negative in front of it, the other one has a positive in front of it. When I look at the 3y squares, you can see the 3y squares will cancel each other as well. So then this will be satisfied. What is the volumetric flow rate between two streamlines that pass through 0, 0 and 1, 3? The first thing that I'm going to do here is I'm going to find my stream function. From the stream function, I'm going to go to the streamline. After I find my streamline, we cover the equation that relates the volumetric flow rate to the streamlines. So I will have to exercise all components of what we covered. Okay, let's go ahead and find our stream functions. Well, we do know that the velocities and the stream functions are related by these two equations in Cartesian coordinates, right? I'm going to insert U, which is 3xy squared minus x cubed will be equal to del psi del y, right? So if I follow this methodology, I'm going to get myself a psi of, well, it's going to be xy cubed minus x cubed times y plus an f of x, right? Because as we mentioned before, this is y, so I will have to have x over here. Okay, so this is my stream function, and you can note that this stream function is a function of f of x. What I have to do is I have to insert the stream function from here to here, and v is given in the question statement, so I have to equate them and see whether I can get myself an f of x. Okay, so that's what I'm going to do. All right, let's go ahead and do it. Well, v itself was given to me as 3x squared y minus y cubed in the question statement. That is equal to minus del x of the stream function. So that will be 3xy cubed minus x cubed y plus f of x, and see where we'll end up with. Okay, the left hand side stays the same, and the right hand side will have a negative parentheses in front of this partial. And what I'm going to get is I'm going to get myself a y cube, and I will get here minus 3x squared y plus f prime of x, and I will say here f prime of x is equal to d of x dx, as we discussed before. So you know why we used derivative as opposed to partial here, because we have only one variable over here. Okay. Well, if I look at this equation, you can see these y cubes will cancel each other because there's a minus in front of it, and these two terms also cancel each other. So from here I got myself an f prime of x is equal to 0, and we have practiced this before as well. From here I'm going to get myself an f of x is equal to a constant value of c. Okay, now I'm going to insert the f of x is equal to c into the stream function equation, and I will get myself xy cubed minus x cubed y plus a constant of c. So this is my equation for the stream function. The next step is finding the streamline from the stream function. If we remember, the stream function is like this, right? It's a function of x and y. However, for the purposes of defining the streamline, what we're saying is this now will be a constant value. So I'm going to call this a, just arbitrary letter, right? So what will happen is that a will be equal to, which is a constant number, will be xy cubed minus x cubed y plus a c. So now you can see I have an arbitrary constant, I have another arbitrary constant. Can I just go ahead and combine them? Yeah, I can. And I'm going to combination of that, I'm going to call this, let's call it s, is equal to xy cubed minus x cubed y, where s is equal to a minus c in this particular equation, right? Okay, and we also introduced an equation for this. This s2 minus s1 will give me the volumetric flow rate. Okay, now what I want to do is let's find out what s2 is and s1 is. The 2 points that is given to me is 1, 3 and 0, 0. What I would like you to take a note is that S2 is the upper streamline, right? So then I will just simply insert the values into the equation. So S2, which is obtained by 1, 3, will be obtained 1 times 3 cube minus 1 cube times 3, right? So that will be 27 minus 3 is 24, right? And if I calculate S1, 0, 0, that is in fact a little bit more easier, as everything is 0, and I got myself a 0 as well. So from this section, I get myself S2 minus S1, and that turned out to be 24. So that is my answer, okay? I don't know the unit of it, so I'm not going to go ahead and say in terms of the SI or British gravitational, okay? So I'm going to leave it at 24. Okay, part C of the question asks me to find the velocity potential, okay? Before we find the velocity potential, we have to check whether this flow is irrotational or not, okay? For 2D flows, this was the only equation that we have to check, okay? And this particular case is 2D flow. So then this will be del y of u, which is 3xy squared minus x cubed, is it really equal to del x of 3x squared y minus y cubed, okay? The first partial will give me 6xy, right? And I'm testing whether this is equal to the right hand side. And the right hand side, when I take the partial with respect to x, is going to give me 6xy as well. So you can see that this is satisfied. So this flow is irrotational. After I establish this, I will go ahead and find my velocity potential. Okay? So the relationship between the velocities and the velocity potential is this way. So I will start with one equation, just like I did for the stream function. And I'm going to insert the u is equal to 3xy squared minus y cubed is equal to del velocity potential del x. And from here, I will obtain my velocity potential as 3/2, right, x squared y squared minus x to the power of 2 divided by 4 plus an f of y, right? Because x is over here, this has to be y, the other variable that we didn't account for yet. Okay, So we established that y is a function of f of y. So let's go ahead and find my f of y as well. And what I can do is I can simply insert it to the second equation that I didn't use yet, the v and the phi. The process is very similar to finding the stream function, right? So I will go ahead and find it. The velocity in the y direction in the question statement was given to me as 3x squared y minus y cubed, right? And the del x of this 3/2 x squared y squared minus x to the power of 4 divided by 4 plus f of y. So let's find out what happened. Okay, v is 3x squared y minus y cubed, and this is partial with respect to y of the velocity potential that I already have of, right, plus f of y. Okay, so the left hand side stays the same, and the right hand side, when I take the first terms partial with respect to y, I'm going to get myself 3x squared y. The second term is not a function of y, so that vanishes, plus f prime of y, right? And f prime of y is equal to dfy dy, right? You can see that these two terms are the same, so this vanishes, and I get myself, and f prime of y is equal to minus y cubed. So if I go ahead and take the integral of it, I will get myself f of y is equal to minus y to the power of 4 divided by 4 plus an integration constant of c. So then if I go ahead and write my final equation for the velocity potential, I will obtain 3/2 x squared y squared minus x to the power of 4 divided by 4 minus y4 to the 4 plus a constant of c. So this is my final equation for the velocity potential.